Hello, everyone. So I'm going to be telling you about demons in physics. I'll spend the first half of the talk recounting some of the famous demons that you might well have heard of that have appeared in physics, and I'll explain why they're called demons and what property something has to be thought of as a demon. And then in the second half of the talk, I'm going to tell you about some ongoing work that I'm doing with some collaborators, where we're looking at a new type of demon that was discovered a couple of years ago, what's called Plains demon. So it's kind of a talk of two halves, but then I'll come back at the end to discuss whether it's a demon in the same sense as the earlier demons. So let me start with a classic demon, and in fact the one that lends its name really to all the other demons. This is the origin of demons in physics, and this is Maxwell's demon. Has anyone heard of Maxwell's demon? A few people. This was Maxwell's demon, by the way. My friend Bruce Gordon drew this Maxwell's demon. He appears in my book. So Maxwell's demon tells us something about the second law of thermodynamics. So the first law of thermodynamics, people will be familiar with. It's the conservation of energy, that energy can't be created or destroyed, just converted from one form to another. The second law of thermodynamics tells us that in spontaneous processes, so those are things that really happen in our world, the entropy of the universe increases. So entropy is a kind of technical definition of disorder. So the example I like to think of is something like an egg rolling along, say, on this podium and falling off and cracking on the floor. So it obeys the first law of thermodynamics because energy is conserved in that process, right? The egg has gravitational potential energy when it's up here on the podium, and then that converts to kinetic energy as it falls through the air. And then it hits the floor and it converts into vibrations, say, that pass through the floor, and you hear the crack sound, so you hear the vibrations traveling through the air, and so on. So energy is conserved in that whole process. But energy would also be conserved if the reverse process happened, if a cracked egg on the floor spontaneously reformed and jumped back onto the podium. But we never see that one happen. So it might seem like that doesn't conserve energy, but of course it does. In the same way that if the egg falls and cracks and the vibrations spread out and so on, it could be the case that some random configuration of vibrations travels through the floor, hits a cracked egg in just the right way to cause the egg to reform, all the bits of shell fly together in the right way, and the thing gets thrown back up onto the podium. Now that's allowed by the first law of thermodynamics, but we never see it happen. So we have another law that tells us that sort of thing doesn't happen, and that's the second law. Okay? And so basically it's telling us that in any process that happens in the universe, the amount of disorder increases. So eggs crack, but they don't uncrack. So you might object, well, if I tidy my bedroom, it seems like I can just decrease the amount of disorder in the universe and there's no corresponding increase to balance it out. But the second law of thermodynamics tells us that there is always a corresponding increase. And you can see that that's the case. If I move around cleaning up my bedroom, I'm doing physical work, I'm using my arms and so on, I heat up a little bit, I heat up the air, and the net amount of disorder in the universe has increased in that process, even though I've made some of it more ordered. Okay? Similar with your fridge. Your fridge can cool things down, they get generally more ordered, but in order to do that, it has to kick out a load of heat out the back, so that in total there's more heat created. So that's the second law of thermodynamics. And in 1867, James Clerk Maxwell came up with a thought experiment, so a sort of imagined experiment, which raised some questions about the generality of that second law of thermodynamics. And his conclusion was that it's only a statistical fact. It's incredibly unlikely for a broken egg on the floor to spontaneously reform and jump back up, but technically, we can deduce from his argument it must be possible. So let me go through his argument, and I'll explain how we've interpreted it since the work of Maxwell. So Maxwell was thinking of having a box with a gas in it. He was thinking of fast and slow moving particles. I prefer to think of it as having a purple gas in it. But when we zoom in and look really close down onto the microscopic scale, our gas is actually made up of an equal mix of blue and red molecules. Okay? So obviously there's going to be a lot more molecules that I show here. That's the idea. So the idea is that if I have a purple gas, it's an equal mix of these blue and red molecules. Now, I could also have a gas where I've got the same molecules, but I only have reds in one half and blues in the other half. And if I started with that situation, maybe with a partition down the middle, then I took the partition out, you would imagine that the red and blue would mix together to give purple. Does that sound reasonable? Okay. And if you think kind of microscopically, the reason that would be happening is that there are many more ways to have the molecules evenly distributed on average than there are to have all the reds in one half and all the blues in the other half. Technically, that's possible, but if you think of all the possible ways they could be arranged, and they're kind of flying around and mixing up, then it's much more likely you're going to find the purple gas than the red gas and the blue gas separated. But Maxwell had the following argument. He said, okay, let's take our purple gas and stick a division down the middle, like this. So we've got two purple gases in the two halves. But now he says, imagine there's what he called a finite being who sits and has control of a little window in the two halves. So this is what's going to get called Maxwell's demon, although Maxwell called it a finite being. So the demon has control of this little opening. He's controlling it with his tail in this picture. And he's watching the gas molecules. And when a red molecule is trying to pass from left to right, he opens the little door and lets the molecule through. But when a molecule is trying to pass from right to left, he's going to close the door and stop it from going through. So this demon is what is now called Maxwell's demon. It's, it's supernatural in some sense. Like, we can't do this. We can't operate on the scale of single molecules like this. So it needs some kind of supernatural powers. It needs to be able to view individual molecules, see where they're going. And it also needs to be able to open and close this door without creating some other kind of heat in that process. So Maxwell asked us to accept these conditions in his thought experiment and sees where it leads us. Well, if the demon keeps doing this, it's going to keep letting red molecules pass right to left, and it's also going to let blue molecules pass left to right, but the reverse processes it won't allow. And you'll see that the end result of this then, of course, is to separate the gas into red and blue parts. And so if there were such a demon acting on a microscopic scale, then the end result would be that I've ended up separating my purple gas into red and blue. And so Maxwell's, so if we zoom back out again, the effect of this, if there were a demon on this small scale, would be that my purple gas I started with would simply end up looking like a red-blue gas like this. Okay, and this would seemingly happen spontaneously. So Maxwell's deduction from this is that the second law can only be statistical. It's incredibly unlikely that a purple gas will spontaneously separate into red and blue, but strictly it has to be allowed. There are many reasons the second law of thermodynamics is very interesting amongst the sets of laws of physics. One of them is that it's, aside from certain quite obscure particle physics processes, it's the only law of physics which distinguishes things going forwards in time and backwards in time. So if I showed you a video of some other physical process, a good example is, say, two snooker balls colliding and bouncing apart. If I showed you a video of that process, you couldn't tell if I'd shown you the video running forwards in time or backwards in time. Both of those would be legitimate things to be happening, balls bouncing like this or balls bouncing like this. And that same property is true for all our laws of physics, except for the second law of thermodynamics. So if I showed you a video of the egg rolling along the table and dropping off and cracking, you know that's the direction in which the video is playing. If I showed you one of an egg spontaneously reforming and jumping up onto a podium, you would suspect I was showing you the video in reverse. So it's very interesting that Maxwell is saying that that law is only statistical, because then your deduction would have to be that there's a very unlikely but technically possible scenario in which things appear to be running backwards in time. So as a result of this, in the years since Maxwell came up with this theory, we've come up with a number of ways to try and eliminate the demon, and we can say exercise Maxwell's demon. The name, I should say, came a few years after Maxwell. So Maxwell was writing about his demon in the 1860s, in 1867 in particular. He wrote a letter referring to his finite being. It was his friend Lord Kelvin, or William Thomson, who named it a demon, for reasons I'll come to in a second. So in the years since Maxwell came up with the idea and said that the second law is only statistical, we've come up with these other arguments that try to exercise the demon. And one is to say, let's go back and take another look at the demon here. So we're saying that the net effect of this demon's operation is simply to separate the gas from purple to red and blue. But people have said, well, that's not really fair, because something else has changed in the universe that we need to control. And that is the fact that before the gas is separated, the demon has no knowledge of the particles and where they are. But at the end of the process, the demon remembers all the processes for where it had to open the door and close it and so on. So strictly, it's an unfair comparison. The demon's brain has been updated so that it has this knowledge of what it's done in the process. And to make a really fair comparison between those cases, we should delete all the information in the demon's brain. So this has led us to the conclusion that deleting information necessarily has associated with it an increase in entropy or disorder. So heat is released whenever you delete information. And this is something we accept in physics these days. So this places a fundamental limit on the operation of computers. At the moment, computers are much less efficient than this, so there's other things going on. But your computer has a big fan on it, it's kicking out heat out the back, or all these data centers in the world, it's costing us a huge amount of energy to remove the heat out of those data centers. Now, partly that's inefficiency, but there is also a fundamental physical limit on the amount of heat that must be produced when you try and delete information. So either you just keep storing it forever and you have to build more and more hard drives to store it, or you delete it as you go along and then you must be creating heat. And we've deduced that as a result of the thought experiment with Maxwell's demon. You could also say, well, okay, I don't want to do that. I just want the demon to keep doing its business and I'm never going to make it delete the information. Well, it's not really a fair comparison then. You've really gone from a purple gas to separated red and blue, but with a knowledgeable demon. But also there's another limit we've deduced, which is that you can't keep doing this forever. If the demon has a finite size of brain, we also deduce that there must be a maximum information density in the universe. You can't keep putting in information forever. And the maximum density is achieved by black holes. So in a sense, you could sort of keep piling in information into the demon's brain if you refuse to ever delete it to try and get around the second law of thermodynamics. Then eventually it's going to form a black hole and its brain will collapse and so on. So I should say all of these things are somewhat, they're real deductions people have made, and especially the creation of heat by deleting information is something that is widely believed in physics. But they're both kind of conclusions that are beyond what Maxwell deduced. And some philosophers have kind of raised concerns with these things and say, well, they're not necessarily helping you with the problem of Maxwell's demon, and that all you can really deduce is what Maxwell himself deduced, which is that the second law is statistical. Okay, so that's the first of our demons. It was named a demon by Lord Kelvin. And so what people typically say is that Maxwell wouldn't have called it a demon because he was very religious and he would have been kind of offended by the idea of a demon. I think that can't quite be the reason, because his friend Lord Kelvin was also very religious and chose to call his demon a demon. But Kelvin was very clear on why he called it a demon. In fact, he wrote a letter to nature to explain it, presumably because people have been taking offense at being called a demon. And he said he didn't mean demon in the sense of a sort of malevolent Christian being. He meant it in the kind of ancient Greek sense, which I think is pronounced like daemon. And okay, he didn't say the precise sense in which he meant that. But I'd say there are I've looked into it, and I think there are kind of like three senses in which things can be sort of demonic or daemonic in ancient Greek. So in the earliest use of the phrase, and I should say some of this is debated by historians, but there was a kind of belief that people didn't act under their own free will. They didn't feel like they were going around doing things because of their own internal thought processes. They acted upon the instructions of God that they were unable to violate. So they thought they were literally kind of walking around and acting because the gods were making them do so. So some people debate whether people really thought that or not, but it's certainly claimed. I think the strongest form of this claim is by a neuroscientist in Princeton who's called Julian James. He wrote this really interesting book where he claims that people not only didn't have free will before a certain date, but they also weren't actually conscious, and that they really acted upon spoken instructions they thought they were hearing coming from gods. And it's a very interesting claim. He also claims that the date on which these things switched was about 2000 BC, so it's like very recent. And he claims this by looking at old texts, sort of like Homer and so on, and saying, well, actually, if you look at it, nobody ever claims to be acting under their own kind of thought processes. They're always just saying, someone went off and did something because the gods told them to do it. And so he says, well, maybe you should take this literally. Maybe people really felt like that. It's a very interesting thesis. I think it's not widely accepted, or maybe some people do. So that's a strong version of the demonic claim that people are just acting because gods are making them act. But a later sense of the phrase daemonic was that gods don't literally come in and control people's bodies. Instead, they have a kind of lower tier of gods. I don't know how you want to phrase it, sort of spirits or something. And if the god wants you to go and do something, they have this spirit, it's called the daemon, who kind of gives you a feeling about something. So you might say, well, why did you run away? I ran away because I was scared. And why were you scared? Well, like the daemon of fear sort of entered into me and gave me the sense that I should do actions that correspond to fear, something like that. Okay, so there's this later idea that the gods don't literally control your actions, but they do sort of send these lower spirits that give you a sense of what you should be doing, and then you go and do it. And it's that sense, I think, in which Kelvin was referring to demons or daemons. So in that sense, the daemon is some kind of entity. It's not necessarily malevolent. There wasn't any sense of that, but they're kind of acting as an intermediary between this unseen world of gods and the world we're familiar with that we move around in. Okay. And so in some sense, these are kind of older ideas, but they do kind of match up with what you might associate with demonic possession or something. If you said you've been possessed by a demon, either the demons literally controlled your actions and so you weren't responsible for them, or maybe the demon gave you a sense of doing something a bit naughty and you were unable to resist it. It didn't give you those precise instructions as to how to go about it. So both of those are these kinds of senses that we used in the Greek sense, but Kelvin was clear he's not talking about Christian demons. He's just talking about some kind of entity. They are personified, so there is some sense in which they're kind of a being of some form. But it's an entity that that connects some unseen world to our seen world. And that's what Maxwell's demon's doing, if you think about it. That's the sense he was meaning the phrase. So Maxwell's demon in this case is not connecting the world of the gods to the world of man, but the microscopic world of individual particles, which was completely inaccessible to people in the mid-19th century. Is connecting that to the familiar world we see. So we see a purple gas or a red and a blue gas, but we can deduce properties on the microscopic scale, and the demon acts as an intermediary between those two. It's doing kind of useful tasks, in a sense, behind the scenes. Okay, so that's what Kelvin meant by it. I wanted to, so Jeff over here is going to give us a quick demonstration. So demons, the phrase demon is used with regard to computers. So I'm just going to quickly bring up, here you're seeing the system processes running on the computer over there. And you'll see words such as daemon or demon appearing all over the place. You see? I don't know if you can see that. D-A-E-M-O-N. So in computer programming, a daemon is some kind of useful program operating in the background. And it's known why these things are called demons, of course. And it was some researchers in MIT in the 60s who coined the phrase. And they'd understood the same thing that Kelvin meant with Maxwell's demon. So this phrasing was inspired by Maxwell's demon. And they thought, well, just like Maxwell's demon is kind of doing a useful thing in the background and connecting this world that we don't see to the world we do interact with. That's kind of what they wanted these demons to be doing. So they're doing useful system processes, but things where you could do it yourself if you needed to, but you don't really want to be doing that all the time. Okay, so they're doing kind of helpful things that you don't have to worry too much about. And again, it's connecting, in this case, the kind of microscopic world of what the computer's up to, like under the hood, to your interactions with it. Thank you, Jeff. That's enough of that one. Okay, so this connects us quite nicely to the second demon in physics, Laplace's. So the reason there's a connection is that the presence of demons in computers is actually quite old. Okay, it goes to the 60s, but earlier than that, there was this sense of, often claimed to be the earliest computer programmer was somebody called Ada Lovelace, who was working with Charles Babbage, who made this kind of mechanical computer, or rather he designed a sort of mechanical computer. I'm not sure any functional one was ever actually built. But Lovelace was the first computer programmer, and she'd been taught by somebody called Mary Somerville, who is the first person to be named as a scientist. So Somerville was a kind of popularizer of maths. She did a lot of mathematical work herself, and she tutored Ada Lovelace, who came to be the first computer programmer. But Mary Somerville also translated some of the works of Pierre-Simon Laplace, who was a French philosopher and mathematician. And the work of developing the earliest computer by Babbage and Lovelace was inspired by Laplace fairly directly, and in particular by his demon. So Laplace's demon, as it's now called, at the time it wasn't called a demon, it was, Laplace referred to her as an intelligence. He's quite clear that his demon is female, by the way. So he refers to her as an intelligence. The French language kind of forces, if you want to call it an intelligence, it has to be female, but he also used female pronouns everywhere else. So it's clear he thought of her as a woman. So his imagined demon, as we now call her, he thought about, I think she was probably quite a good thing rather than an evil thing. She had the ability, again, to look at the microscopic world and see what individual particles were doing, much like Maxwell's. But in Laplace's case, he was saying, okay, so imagine this entity exists, this intelligence, and she knows at some instant the positions and velocities of every particle in the universe, but just at that instant. Then surely she can deduce all future positions and velocities. She's very clever, she's an intelligence. So she can work out exactly how everything is going to be in the future because she knows everything at this instant, right? If they're all just like little particles bouncing around and so on, then she must also know what's going to happen in the future. And she must also know everything that happened in the past, again, by looking at where they are now. And so this is argued to be the first clear statement of scientific determinism. And that's what inspired the creation of the computer. Babbage and Lovelace and others were thinking, well, if that's true, then I ought to be able to calculate what's going to happen in the future, much like Laplace's demon or his intelligence, right? But this kind of runs it against certain ideas, it runs up against free will. I feel like I have some agency in what I'm doing, and so therefore it shouldn't be predictable based on just like taking a snapshot of the universe, what I'm going to do. I feel like I have a choice, right? So it opens up those kinds of questions. At the time, it was kind of controversial because people said, well, doesn't this cause a problem with the existence of God? And there's a famous quote that's attributed to this. Supposedly, I think there may be some like apocryphal elements to this, but supposedly Napoleon spoke to Laplace about this idea. And Napoleon said, where does God fit into your theory? And supposedly Laplace to this replied, sire, I found no need for that hypothesis. I didn't have to put the hypothesis of God in to get my answer out. So, read into that what you will. So it did cause some controversy, I think, but it was also very inspirational. People thought, okay, the universe seems to be deterministic. This inspired the early development of computers, and those ended up having demons in them, perhaps inadvertently naming them after this earlier demon. So with Laplace's demon, that's kind of the origin of this scientific determinism. Some people say it's kind of obsolete these days, that it's been sort of exercised by quantum mechanics, which says that the universe isn't really deterministic after all. I would question whether it really has been exercised or not, or she has been exercised. But I can give you the demonstration of the non-deterministic nature of the world. So if we switch over to the camera, please. Thank you, Jeff. So in a sense, this could have been seen before the time of Laplace. What I have here is just a crystal called calcite. And calcite has a very interesting property that if you put it over some letters like this, you see two copies of the letter. Do you see that? If you look maybe at the E there, you see two copies of the E. And if I rotate the crystal, one of those copies will rotate around the other one, closing up at certain angles as I keep going around. There you see them quite separated. And there you see them closing up. So one kind of dances around the other as you rotate it. Do you see that? Maybe? Okay. I'll pass it around actually, so have a closer look. Yeah. Take a look yourselves. So this is an interesting property called birefringence. And if you think of the world, think of light as being conveyed with a beam of light, then this makes perfect sense. The light enters a crystal, it can split into two beams, and I see two images. Fair enough. But if you wanted to say what's the world like on the microscopic scale, what would happen on smaller scales in that process? Well, you're asking the question, what's the beam of light made of? And of course, the answer is going to have to be something like a particle, okay? Some kind of thing that's indivisible in some smallest part. And if you believe that, that's perfectly acceptable, and it was believed in before Laplace. Newton referred to these things as corpuscles. So we now call them photons of light, individual particles. But if you believe in photons, then you get into trouble with the calcite, because now you're saying that, well, I shine my light into here, it's a stream of individual photons, and each one has a choice as to whether it goes up or down. And that's why you're seeing two images. But this seems to go against the idea of determinism, because it's saying, well, I can set up an identical experiment, shine the photon into the crystal, and under exactly the same conditions, it could do either that or that. So actually, the seeds for this non-deterministic view of the universe were laid a lot earlier than Laplace's idea. But whether it really rules out determinism or not, I think is less clear. So we have a proper quantum theory of what the photon is up to now, and we've kind of changed our position. We say now that we can only give probabilities for things to happen. But those probabilities actually evolve deterministically. And then something very mysterious happens when we measure. And then there's this very big open question in physics of philosophy as to what exactly happens when we measure quantum mechanical things. And that's something we still haven't answered. So in a sense, Laplace's demon, I think, is still with us, but in a new form. So those are two important demons in the history of physics. The third one I'm going to mention, and the last in history, is Descartes. So Descartes is unique in this case in the sense that he almost literally did refer to a demon. And it was in his kind of original set of arguments that led to his famous quote, "I think, therefore I am." And so this was the basis of scientific skepticism, the idea that we should be skeptical of claims until we've kind of rigorously justified them somehow. And he said, okay, what can I really be certain about in this world? And you might think you could be certain about your senses, like the things I'm literally seeing and feeling right now. But he said, well, I can't actually even rely on that, because he says there could be some, what's now called an evil demon, that's how we tend to translate it, there could be some evil demon which has made it seem like all these things are reality, but they're not, it's just me being tricked. You know, the modern version of this is the film The Matrix, where everyone thinks they're living in the world, but really they're living in a pod and the world is being simulated. So really he come up with the same idea. So his end conclusion, though, was that, well, even if it's all fake and I'm not really feeling and seeing those things, I'm still having the thought about feeling and seeing them. So I can start from that one basic assumption, I think, and therefore I am. That's two things I've got at that point, and then I can try and build from there. So Descartes, he wrote in French and also in Latin, and in both cases he used a phrase which was kind of like genius to refer to this thing. So I asked someone who knows Latin about this, and they said, well, genius in that sense, it does mean intelligent, like it does now, but it means kind of cunning as well. So we should think of it a bit like genie, and I think the root of the word genie is similar. So a genie is very powerful, right? They can grant wishes for you and so on, but they're also very tricky. Like you have to get your phrasing right or they try and mess you around. So I think that's the same sense in which he had this evil demon. It was a genius. So super clever, very like supernaturally powered, and also a little bit cunning. Not necessarily evil, but a bit dodgy. So they've been with us since the start of physics, basically, with Descartes and then Laplace and then Maxwell. And in each case, they underlie a very important principle that we have in physics and also in science. And their naming, okay, it depends on the demon, but basically a lot of we have other demons as well, but typically they were called demons much later than they were invented. And I think Maxwell's was the first that was properly called a demon, not by Maxwell, but by Kelvin. The others got named retrospectively. Okay, so I'd like to tell you now about some ongoing work in which we've been involved in looking at a new type of demon. And initially it's going to sound like a totally unrelated type of demon, and arguably that is the case, but I'm going to come back at the end and discuss whether it's really the same type or not. So it's called Pine's demon, and rather than being some supernatural entity that does something helpful behind the scenes, Pine's demon is instead a type of particle, and a particle that was discovered 2 years ago in 2023. So before I go further, I should first explain what a particle is. So this is just a definition I've come up with, but I think it sort of captures what we mean by it. I'd say a particle is something that can exist by itself in the vacuum of space and cannot be reduced to other things with that property. Okay, so it gives you the sense of it. So I could say, like, I can have a particle of light, and that's what we call a photon. A photon can exist by itself in the vacuum of space, shooting along. It can't be reduced to other things. It's not made up of smaller bits. An electron, similarly, that's another example of a particle. An atom, say, that can exist in space by itself, but it can be reduced to other things that can also do that, namely electrons, protons, and neutrons. So an atom is not a particle. Okay, so that's a basic definition of what we mean by a particle. So all of those actually are what we call elementary particles. They're things that you study in the standard model that you might go look for in CERN and so on. But I work in a different area of physics to that. I don't work in particle physics. I work in what's called condensed matter physics or quantum materials. And this is like the study of stuff, like things like this, stuff in front of you, crystals, that kind of stuff. And in that setting, we get a different type of particle, what we call an emergent quasi-particle. So the way to think of this is take some crystal, like the one that's being passed around at the moment, and imagine like an electron's flying along and it flies into the crystal. What's going to happen? Well, the electron's going to interact with the stuff that's there, right? The crystal's made of atoms. The atoms have electrons of their own in there. They have positive nuclei and so on. So the electron flies into the material, it interacts with all the stuff that's already there. And you might think, what's the end result of that? Maybe it's just a total mess that's quite hard to describe. But remarkably, actually, it ends up emitting a description that's very much like the electron that went in there, but some of its properties have changed. So its mass might have changed. And in some senses, its charge can also kind of change. Now, it's not that the elementary electron has really changed its properties. It's just started interacting with other stuff around it, and it still emits a description that's very much like it used to be, but slightly different. So by analogy, you could say, well, if I want to, say I take a ball and I want to know the mass of this ball, well, I can use Newton's second law, force is mass times acceleration, and I can try and shake the ball and see how much force is required to get a certain acceleration. You could use that to work out the mass. And then I could do that same experiment in a swimming pool. And of course, it's now going to take a lot more force to get the same acceleration. So I might deduce that the ball's mass has increased. I wouldn't usually. I'd say, well, really, it's not a ball anymore. It's a ball underwater. So I'm having to push against some of the water as well. Okay. But that's the same thing you should hold in mind. When the electron flies into a crystal, well, it starts interacting with the other stuff. And if I try to measure its mass somehow, then I'm really measuring the mass of that plus the interactions with the other things around it. Okay. So we call these quasi-electrons, and they don't need to be things that have flown into a crystal. They could be the electrons that just live naturally in a crystal. So another example of a crystal is a metal. Basically all metals are crystals. What I mean by crystal, by the way, is just something with a regular periodic arrangement of atoms on a smaller scale. So metals are examples. The calcite crystal that's going around is another example. So metals are crystals, and they have electrons in them already. And those electrons do not necessarily have the same properties as an electron outside of the material, okay? And in particular, their mass could be different. So we call those quasi-electrons, but actually almost always we just call them electrons. We need to bear in mind that their properties might be different to the ones you would detect if you could find them by themselves. Okay, so there are other types of emergent quasi-particles. That's one example. My favorite example, by the way, is a phonon, which is a particle of sound. So a particle of sound couldn't exist in the standard model of particle physics. It can't be the type of particle I described before, because my definition was that it has to be able to exist by itself in a vacuum of space. But sound can't do that. Sound can't travel through space, whereas light can. Okay? So there's an elementary particle of light. There isn't one of sound, but sound can travel through crystals or the air and so on. And when we describe the passage of sound through a crystal, we can describe it perfectly well using quantum mechanics, and we say that it's conveyed by particles. And those are what we call phonons. Another example was proposed in the 1950s by David Pines. And the first one is not going to be Pines' demon. It's what's called a plasmon. So Pines also proposed the idea of plasmons. So there's a lot going on in this plot, and you don't have to worry about most of it. I've taken it from this quite recent paper. You see that the phrase plasmon keeps appearing here. So a plasmon was back then a new type of particle that had never been discovered before. It can only exist inside materials, and in particular, it exists in all metals. And the idea is that inside a metal, the metal is bonded together because we take some atoms, you stick them together. The atoms each lose some number of electrons and become positive ions. And then those electrons that they've given up form a kind of delocalized sea, as we call it. Okay, so they sort of float around amongst the positively charged ions, and that holds it all together. But because of that, the electrons are kind of free to do stuff. And in particular, if you connect electrodes to it, you can pass an electric current through a metal because the electrons are free to carry the current. But you can also say, well, I've got a load of electrons kind of acting, maybe think of it like a sea. Well, then I can get ripples in that sea by itself. I don't have to pass a current through it. It can also just get wobbling by itself. And that's what a plasmon is. So we'd call that a plasma oscillation. The phrase plasma, by the way, you've probably heard of we've got these three states of matter: solids, liquids, and gases. Some of you might have heard of the fourth state of matter, plasma. We've heard of that? Okay, good. So a plasma is an ionized gas. So it's gas that's become so energetic, the atoms have lost some electrons to become charged, and you've got like positive and negative charges floating, and it'll carry a current. But of course, that's exactly what's happening in a metal. So the electrons in the metal are forming a plasma. It's a charged gas. So you can have oscillations passing through that. It's a kind of collective behavior of the electrons. And we can give that a quantum description. And the quantum description of those oscillations in the sea of electrons is what we call plasma. The point of this picture, by the way, is to show that this description in terms of particles is not just one way to think about it, or you could also think about it as a collective behavior. It's really actually a meaningful thing to be saying. So what they're showing in this plot is they're firing electrons, I think, at a thin film of aluminium, so metal. And they're either seeing which electrons reflect off or which ones pass through the metal. You get the same sort of plot. And it's as a function of the energy of the electron that they're shooting in. This is what's called electron energy loss spectroscopy. And you see that there's a peak at 0 there initially, and then there are peaks that are basically evenly spaced as you move along. This even spacing is the important thing. There's a load of other stuff going on. There's some background we don't need to worry about. But the point is there are these spikes that are evenly spaced. And so our interpretation of this is that we're firing an electron in, and it's interacting with these plasmons, these other particles that exist inside the material. And so, for example, the electron can it could go straight through, and that would be the first peak, or it could pass into the material and it could scatter off a plasmon, one of these emergent quasi-particles that lives inside the element. And then it can carry on its way, and then maybe it scatters a second time. So each time this happens, its momentum and its energy are changing because it's transmitting some into these other particles. So the even spacing of those peaks is direct evidence of the particle nature of these plasmons. Okay? And again, they can't exist outside of metals, but every metal has them. So Pines proposed plasmons in the early 1950s. In 1956, he proposed another type of particle, what's now called Pines demon. And so this exists in some metals. So I said that inside a metal, the electrons can have different properties, the mass might be different. In fact, they can have multiple different types of electron in the same metal. Not all metals do this. For experts in the audience, you need multiple different Fermi surfaces for this to happen. But there are many metals that do have that. And Pines said, in those cases where we have multiple types of electron, so they might be two distinct species that have very noticeably different masses, but the masses of each species is basically the same amongst them. When you have that situation, he said, you can have another type of particle. It's clearly related to the plasmons. And if I show you, so we were shooting electrons through that film before, right? And I said they have the momentum of the electron is going to change, and its energy is also going to change. And we can detect both of those things. So in the simplest experiment, you just detect the change in the energy of the electron. More recently, we've got this new technique called momentum resolved electron energy loss spectroscopy. And you can measure the change in the momentum of the electron as well. And so you work out that these particles inside the material must be taking whatever change you've seen in your beam you're shooting through. That must be manifesting itself inside the material. So the first plasmon I just told you about is called an optical plasmon. The reason for this is that if I were to shine light at a metal looks shiny, right? Famously, all metals will look shiny. What's the reason for that microscopically? Well, light is an electromagnetic wave. It has an oscillating electric field. It comes in, and that oscillating electric field is going to oscillate the electrons. They can respond to that. They sort of wobble. And in that wobbling, they generate a new electric field that goes back out again, and they send light back out. So that's why they're shiny. So metals are shiny. They reflect light up to what's called the plasmon energy. So once you increase the energy of your light, which means going to higher and higher frequencies, at a certain frequency, metals become transparent. You can see straight through them. But typically, this is much higher frequencies than visible light. This would be like X-rays and things. Okay, so if you shine electrons through some metal, you can plot the energy against momentum of the things inside the metal, and you'll get this nice curve here. And again, for experts in the audience, there's a gap here. This is what we call mass gap. Because of Einstein's relation, E equals mc squared, energy and mass are related. And so what we can see is that this plasmon that exists in metals has a mass as a particle. Okay, so that's contrary to a photon, a particle of light that has no mass. This second particle that Pines proposed slightly later in 1956 is what's now called Pines demon, although he called it an acoustic plasmon. And so it would have this as a function of energy and momentum instead. It would look very different. So you'll notice that the first one was called an optical plasmon because it interacts with light. The second one is called an acoustic plasmon, and this acoustic sounds like sound. And in a sense, it really is very much like sound. It's quite similar to how the fluid of electrons, that the delocalized C, it can also carry vibrations, and so it can carry sound. And in these materials, it's very similar to sound. It's not quite sound, but you don't go too wrong thinking of it as quite similar to how sound might travel through a gas of electrons. But for technical reasons, you need two different types of electron for this to work. So Pines proposed this back in 1956. Nobody saw Pine's demon, or the acoustic plasmon, for many decades, and it was first observed in 2023, so very recently. Essentially, the issue was that you can try and measure these things, but the energy scales at which you're looking for, I haven't shown you in units yet. These are very small energy scales, and you need a really high resolution in energy to see this. So it's the group of Peter Abamonte in the University of Illinois in Urbana-Champaign has built a brilliant setup that can go to much better resolutions and energy than anyone's been able to get to before. And they believe that in certain material, they've seen Pine's demon for the first time. Now, the work, I wasn't involved in that work. What we've been doing is taking a look at the theory behind that and trying to explain some aspects that, well, I'll show you, but we thought there's something that didn't quite match the original theory. And just to give you a quick idea about that, and this is maybe more for the experts in the audience again, for these two types of particles we've seen before, this is a particle with mass, this is a particle without mass. What we think you end up seeing whenever you look for Pine's demon is actually something that looks like this. You'll see nothing in the standard model of particle physics that paints like that. It looks rather like something called a tachyon, which travels back in time or has an imaginary mass and a negative mass squared. In fact, it's not like a tachyon. I spent a while thinking it was and getting very excited about that because we found particles that go back in time. In fact, my collaborator pointed out that this version is slightly different. So you can't get too excited about that, unfortunately, but there are some hypothetical particles that have that sort of dispersion. This is actually a little bit different. Still, our claim is that this is the real shape you expect to see Pine's demon in real materials. Real materials have disorder, have kind of dirt. So let me show you what it is they saw. And here are the experiments from Peter Abamonte's group. So Ali Hussein was the first author on it, published a couple of years ago. And you see these plots of energy versus momentum. They're shining their beam of electrons in and measuring the momentum and energy as they come out and deducing the property of Pine's demon. And they're a pretty good match. These are their data points and the error bars on them. I've just drawn some straight lines on here. You can do a more precise calculation for exactly what you'd expect to see for Pine's demon. But it's basically a straight line that looks like that. And they're pretty good. But you can see, there's some shape to this curve that isn't captured by a straight line. And they didn't have a good explanation for what that is. Now, it wasn't in Pine's theory, but of course, Pines is proposing this in 1956, and it took many decades to even see the thing at all. So let me tell you about the theory that we've added onto this, just to finish up. Oh yeah, we're right out of time. Good. So the first breakthrough we had is myself and my postdoctoral research associate, Miguel Angel Sanchez Martinez. He's done really all the detailed calculations and numerics here. But the first breakthrough came with my other collaborator, Blaise Goutureau in Paris. And he works on what's called hydrodynamics. So the name, it sounds like it's describing the flow of water, and that is exactly where the theory came from. But these days, people are studying the kind of hydrodynamics, as it were, of the electron fluid. So this is some of the most cutting-edge topics in condensed matter physics and quantum materials. Are very difficult questions to answer in terms of thinking about particles, and they may not even admit particle descriptions. Instead, you have to think about this kind of interacting soup, and then it's much harder to say anything on the small scale. So what we do is kind of revert to these older theories about, well, we've got theories of how water flows around and so on. Perhaps the electrons themselves are behaving in that way, and that's a good way to think of it. So Blaise Goutureau is an expert in the hydrodynamics, and I showed him these data while we were discussing something else, and he said, oh, we get that kind of shape all the time. I should say, I had this idea that the shape kind of went along with it and then came up. And I had one reason for thinking that, which turns out not to be right. But his idea was that hydrodynamics can explain this. And he just wrote down this equation basically on the spot. He said, oh yeah, we get this sort of thing all the time. Let's try and fit it for that. And you see that it fits really nicely. So I would say that it's not a straight line exactly, it kind of goes along a bit on the bottom and then comes up. So hydrodynamics did this really straight away, and the idea is that there's a gap at the bottom there, and that corresponds to there being disorder in the material. So Pines didn't really bother to make this prediction because he was just predicting, what sort of things would this look like. He didn't like add in the sort of messiness of real materials. That requires a bit of extra work. But we think that in real materials, there's always some kind of disorder. The crystals are a finite size. There's all sorts of defects in there. And in fact, the gap here can be measured from other experiments, and it was already known, so that the energy scale was known elsewhere, and we just took those data from existing experiments. So hydrodynamics did a very good job. The two plots here, by the way, it's at 30 Kelvin, 300 Kelvin, so this is close to room temperature. This is a very low temperature. You see the effect in both cases. So we had this hydrodynamic theory. What we really wanted was a kind of microscopic explanation again. It's always what we want to do, go and zoom into the microscopic scale. So with this, my other collaborator, Luke Rademacher, came up with a very elegant mathematical theory that could also explain this. In fact, by construction, actually, it ends up matching the hydrodynamic theory really precisely. And then my postdoc, Miguel Angel, did these very nice calculations for the real material, which end up giving this curve here. So there's a kind of abstract sense in which you can write down the equations, but then you can also make it material specific. And then we got this really good match. And so the idea is that it is hitting all the data points to within the error bars. Out of interest, I just like this picture because it's very beautiful. So Miguel Angel has also calculated the expected lifetime of these particles. So these particles, they can sort of travel along, but they can decay into other things. And you can see that they're very long-lived along these lines, but down here they're very short-lived. So if you're worried about this gap down here, and particle physicists would be, because you say, well, what happens if my particle has that momentum if you don't have a point there? The idea is that the particle doesn't really exist there. So in a sense, the Pines demon has been exercised, but we prefer to think of it as it's a real thing. You can see it, you can measure it. Those experiments did see Pines demon, but the shape of a real Pines demon will actually look like this rather than a straight line. So down here, it's kind of decaying into other particles. So just to finish up, I'd just like to here are my collaborators I've worked on with this, plus Bruce Gordon, who drew Maxwell's demon. I'd just like to say, to return to the first part of the talk, you might say this talk seems to be totally split into two. In the first part, I told you about these kind of creatures who do tasks behind the scenes and led to the kind of historical demons. Why is Pines' demon also a demon? Well, basically, it was a kind of rubbish pun come up with by David Pines. So he noted that whenever we name particles in physics, we always call them something on. So like electron, photon, phonon, plasmon. And he noticed the demon also ends in on. And he basically just wrote in the paper, well, I think it's a shame Maxwell lived too soon to have a particle named after him, because of course, he was kind of important in that thinking about the microscopic and macroscopic scales, but he lived too soon for us to have direct access to it. So he said, I think we should name it a demon in Maxwell's honor. And then subsequently, of course, it ended up being referred to as Pines' demon. So you might say that's just a rubbish pun, but I'd actually say it's maybe inadvertently deeper than it intended to be. Because there were those two senses of the word demon, right? There was the original sense where demon is sort of the force that literally controls people's bodies and makes them do stuff when gods tell you what to do. There was the later sense that Kelvin was referring to, in which the gods just give instructions to some lower being that then goes and gives you sort of inspiration to do stuff. But actually there was a third stage after that, where it was understood that, or believed that some people of certain standing could become demons upon death. So people got kind of elevated into these lower ranks of spirits somehow, and then they could kind of go and inspire people in the future. So I asked my Greek friend about this, and he said this is a concept that still sort of exists. But if you think about it, it makes a lot of sense. And I think, okay, I might be kind of paraphrasing it a bit here, but basically the daemon or demon in that sense is like some philosopher who's had a school of thought and some followers, and they've changed the way people think about the world somehow. And as a result, long after they die, you might still think of the world in that way because of them, right? So I don't know if this is a good example, but like, Socrates had the Socratic teaching method. Maybe if you're feeling particularly Socratic one day, then, you might phrase that as the demon of Socrates has entered into you and given you a sort of wish to employ the Socratic teaching method, something like that. So maybe it's really just saying when you've had an idea that's profound enough and lives long enough after you that you've kind of become an adjective in some sense. So I think in this sense, actually, Pine's demon perhaps wasn't just a total random joke and disconnected from the other demons. I would say, in some sense, Pine's was quite key in this development of the idea that there can be particles that exist inside matter that can't exist as kind of elementary particles. He wasn't the first person to do this, but he was certainly one of the earliest. And the plasmons and then Pine's demon after it are two very clear examples of these types of things. So in that sense, you might argue, well, Pine's demon is, if I'm feeling like describing the behavior of some lump of matter in terms of individual particles, perhaps David Pine's demon, his daemon, has entered into me and given me a sort of urge to do that, and that's why I'm active. So I'd say in that sense, it actually does kind of connect to the other meaning of demons, somewhat inadvertently. Okay, so I'm going to finish things up there. If you're interested in demons in physics, I'd like to point out the existence of this book. Nothing to do with it whatsoever, but I read it and enjoyed it very much. So it's a history of demons in science, and she goes through a lot of cases, and a lot of what I told you about demons came from this book. If you're interested in the more general topic of stuff that exists in matter that can't exist elsewhere, I have my own book, which covers some of this stuff, including Maxwell's demon. So with that, I will end things there and take any questions you have. So thank you for your time.